Thin film interference is a cool effect. It explains why soap bubbles and spills of oil on water give a cool rainbow effect. Also, it's how they encode information on Blu-ray discs and gaming discs. It all comes down to three main bundles of light. Out of all the light rays that leave the source of light, the sun or whatever the source happens to be, but out of all the light rays that come down and hit the material, I'm drawing the light rays on a bit of an angle so we can see them better, but when we do the math we're going to pretend the light rays go straight in and straight back out. Out of all those light rays that come down, some of the light rays bounce off the actual coating. I usually call those bundle of rays number 1. Other chunk of that light goes into the coating. As it enters new coating, since the coating would have a new index of refraction, it's going to have a slightly different speed and a slightly different wavelength. That light bounces off the material underneath, then passes back through the material and eventually makes it to the observer, to the eyeball. I'm going to call that bundle of light number 2. Whether bundle of light number 1 and bundle of light number 2, whether they make a situation of constructive interference or destructive interference depends on two things: what happens in those reflections and what happens as a result of traveling the extra distance. We're going to say that the coating is a thickness of letter T. So bundle of light number 2 goes T on the way down and T on the way back up, or 2T altogether. I'm showing it on an angle so we can see it better, but we're going to pretend like the light ray goes straight through T and straight back up. I'm going to treat thin film problems. I'm always going to solve them using 3 steps that always seem to work. The first step is interpret your indexes and calculate that new wavelength. Oops, spelled that wrong. That's supposed to say interpret. Interpret your ends and calculate the new wavelength. As I said, when light enters that coating, it's going to shrink in wavelength a little bit and slow down a little bit. The new wavelength is the wavelength in air divided by the index of the coating. The second step is to compare the reflections. Basically, if only the reflections happened, would those light rays, only the reflections, would those light rays be in phase or out of phase? If the ends are in order, smallest to greatest, then they're in phase. Pen slid. In phase. If the ends are out of whack, then they're out of phase. The last step in my sort of 3-step method is the logic step. If the ends are in the way that the question wants them. So if the question asks for constructive and the ends were in order, so the light's in phase, if the ends are the way they want them, if the answer to that is yes, then that extra distance must be one of the wavelengths. If the ends aren't the way we want them, maybe the ends are in order but the question wants the light to be cancelled out, then the extra distance must be off by half a wavelength. We'll do it together so you can kind of get the hang of it. Kind of a classic example is oil floating on water. The first step is to interpret those ends, so I'm going to doodle a little picture. We've got a thin layer of oil. We're going to eventually say that that's a thickness of T. Its index is 1.5. Underneath that we've got our water. Its index is 1.3. Above it all we've got air. The index of air is 1. Because of the ends, well, first thing I'm going to do is the light that goes into the coating, it's going to slow down and its wavelength is going to shrink. The wavelength in air was 600 nanometers. So when it gets into that coating, which has an index of 1.5, it's going to shrink down to 400 nanometers. Next step in interpreting the ends is to think about those reflections. Bundle of light number 1 is in air and bounces off the coating. Bundle of light number 2 goes into the coating and then bounces off the water. So if we compare 1 and 2, they both reflected, they didn't both. Bundle number 1 reflected off a larger N. Bundle number 2 was in the coating and bounced off the water, so it was in 1.5, bounced off 1.3. So it reflected off a smaller N. If this is all that happened, is the reflections, then these two bundles of light are out of phase, because they did different things. One bounced off a larger N, the other bounced off a smaller N. Now if we go back to the question, it wants the reflection of orange to be constructive. I'll flip to a blank page, but basically constructive interference occurs when light is in phase. Right now the light is out of phase because of the reflecting. So when we consider that extra distance, the light's already out of phase, we want to kick the light back into phase. So the extra distance has to be half a wavelength, kind of like a double negative. The light's out of phase because of reflecting, half a wavelength will put them out of phase again. So out of phase and out of phase will combine to make them back into phase. I made up some nice numbers for this one. The wavelength ended up being 400 nanometers. So you can flip-flop things around. When we get TL by itself, it works out to be 100 nanometers.